Hello class, this lecture will be on electronegativity and bonding. As you remember from our study last unit on the periodic table, electronegativity is the ability of an atom to attract electrons in a chemical bond. If we look at the periodic table and remember what we learned about the periodicity of electronegativity, we'll see that the elements on the left-hand side of the periodic table, also known as the metals, have lower electronegativities than the nonmetals at the right-hand side of the periodic table. And then if you look at any family in the periodic table, as you go down, the electronegativities decrease. So if you look at the table as a whole, francium on the bottom left-hand corner of the periodic table has the lowest electronegativity, and then fluorine on the upper right-hand side of the periodic table has the greatest electronegativity. And remember, electronegativity is the force of attraction that the nucleus of one atom has for shared electrons in a covalent bond. So here we have a covalent bond. And we are now discovering that there are two different types of covalent bonds. So right now we're going to discuss something called the polar covalent bond. Here we have a bond between hydrogen and chlorine. Here's a different view of the bond between hydrogen and chlorine, showing the electrons, shared and unshared. In between hydrogen and chlorine, we see the pair of electrons that are going to be shared. The other 6 electrons are the valence electrons that are not shared. And if you look carefully at the diagram, we see that in this density cloud of electrons around hydrogen and chlorine, the electrons in blue, the cloud on the blue side, is much larger than the cloud on the left-hand side, which means that the electrons are spending more time around chlorine than they are around hydrogen. And since electrons are negative, then the chlorine end of the molecule will be negative and the hydrogen end will be positive. And so when we have a separation of charge, we call that poles. So the hydrogen chloride bond is a polar bond. Chlorine and hydrogen share the electron, yes, but not equally. And this is shown in the diagram. There's a thick arrow showing how the pair of electrons is more attracted to chlorine, and there's a thin arrow showing less attracted to hydrogen. And this is because they have different electronegativities. So the polar covalent bond is when two atoms do not share electrons equally. And we develop partial charges on the atom. The element with the smaller electronegativity will have the positive partial charge, and the one with the greater electronegativity will have the partial negative charge. Another way that we can determine that a bond is polar covalent is by subtracting the two electronegativities. And if we discover that difference in their electronegativity is between 0.5 and 1.6, we can classify that bond as not only covalent, but polar covalent. Now this notation that tells us about partial charge is called delta notation, delta standing for dipole. And I'd like to introduce you to a Greek letter. You might know that capital delta looks like a triangle, and we use it in math to mean the change in or the difference in. The lowercase delta is what you see in front of you. It looks sort of like a squiggle. Stands for partial charge. So in a polar covalent bond, the atom that holds the electron more tightly becomes slightly negative charge, and so we would write the delta negative above that atom, and therefore the other one who has the electrons less will become slightly positively charged. And so here are our delta notations. So here's our polar covalent bond again, and there are our delta notations. Hydrogen, who has the less electronegativity and therefore the positive charge, and chlorine that has more electronegativity and the negative charge. Here's an example. Calculate the electronegativity difference and apply delta notation to the bond between carbon and oxygen. So first, we'll go back to our periodic table and we'll look at carbon and oxygen, and we'll subtract their electronegativities. And then we'll determine the difference. And if that difference falls between 0.5 and 1.6, we know that we'll have a polar covalent bond. Then we'll add the delta notation. On the element that has the greater electronegativity, we'll add the delta negative. And on the one that has the lesser electronegativity, it will be the delta positive. In this case, carbon will be the positive and oxygen will be the negative. Now, we know that there are polar covalent bonds, so there must be nonpolar covalent bonds. The most common nonpolar covalent bond is the one where two atoms of the same type bond. And of course, their electronegativities are exactly the same. So they will share the electrons equally. And if you look at this diagram, we see that this cloud of electrons that's being shared between them is equally distributed. There's not one end that's bigger and another end that's smaller. And so this would be a classic example, Cl2, of a nonpolar covalent bond. And if you think about it, chlorine has an electronegativity of 3.2, so 3.2 minus 3.2 is 0, and that is less than 0.5, which is the cutoff point for being a polar covalent bond. So in a nonpolar covalent bond, two atoms with the same or similar electronegativities share electrons equally. And we do not write the delta notation because there are no charges on the atoms. And in order to classify a bond as nonpolar covalent, if we subtract the two electronegativities, the answer will be below 0.5. Now, how about an ionic bond? Well, you might say, I thought you said, Mrs. Gallegos, that electronegativity is the force of attraction for electrons in a covalent bond, but we can also sort of apply this to the concept of an ionic bond. We know in an ionic bond, and we can see in the diagram, that the electrons are not shared, but they are transferred. And here we see sodium's electron being pulled by chlorine and making its last pair, so it will have an octet. So we're not going to write partial charge because they have real charge. They have real positive and real negative. So we don't use the delta notation. We just write a positive and a negative. So in an ionic bond, we see that the atoms have a huge difference in electronegativity. That's why the nonmetal is able to pull the electron away from the metal. And if we were to subtract their electronegativity difference, we would see that it is greater than 0.6 or even greater than 2. And we will have, in this case, not partial charge, but full charge. And so we would write just positive and negative and not squiggle or delta positive and squiggle delta negative. And so in summary, if we have a pure nonpolar covalent bond, we'll see that the electrons are shared equally. And if we were to subtract the electronegativity of the two elements in the bond, it would fall somewhere between 0 and 0.4. Whereas if we have two nonmetals that are covalently bonded and we subtract their electronegativities, sorry about that, we'll see that we'll have a difference between 0.5 and 1.6. This diagram shows us 2. So there is some wiggle room there. And we'll know that this will classify the bond as a polar covalent bond, and then we'll add our delta notations to show which side of the bond is negative and which side of the bond is positive. Now with an ionic bond, the electron is actually transferred from the metal to the nonmetal, and we have full charges. So we're going to write a minus and a positive. And that is the electronegativity and bond. So here's a nice table that sort of sums everything up. The characteristic: in a nonpolar covalent bond, we have equal sharing of an electron pair. In a polar covalent bond, we have unequal sharing of an electron pair. In an ionic bond, we have transfer. In our example, a nonpolar covalent bond is shown simply with a line between the two atoms who are bonded. In a polar covalent bond, we have delta notation showing which part of the bond will have a slight positive charge and which side will have a negative. And then ionic, we don't show the line because it's not a covalent bond, and then we have full charges. Sodium will lose an electron and become positive, and chlorine will gain it and become negative. And so here's where electronegativity comes in. We can use electronegativity Up until now, we know that we can classify a bond by just looking at the two elements that are in that bond. If it's two non-metals, I know it's covalent. And if it's a metal and a non-metal, I know it's ionic. Well, now we can further distinguish between the two different types of covalent bonds. So if my electronegativity difference is between 0 and 0.5, I can now classify the bond not only as covalent, but as non-polar covalent. If I have an electronegativity difference between 0.5 and 1.6, then I can classify the bond as polar covalent. And then if I have a metal in my bond, no matter what the electronegativity difference is, I know that that compound will be ionic. So here's an example. Why don't you go ahead and pause the video and use the electronegativity chart in your textbook and see if you can classify these bonds as either nonpolar covalent, polar covalent, or ionic.